recently we got some actually nice new results on this also recent paper, which perfectly fits into the algebraic structure of this talk, right? And also fits very well with the talks from yesterday and some of the things mentioned in talks today. And so, yeah, because the algebra. Now, yesterday we heard a lot, and also today in Jens' talk we heard a lot about all sorts of Lie algebras. But in this talk I will be focusing on one very specific one, and that is SU2 to the n. And I forget about all the others in this talk. Basically, it either generates SU2 to the n, or I don't care about it. And I can also phrase it a little bit more relaxed. The question as how many Pauli rotations create all others efficiently? Yeah, and I will describe a little bit more what this actually means. And I think this is an interesting question in and on itself. And I don't really need to motivate it. I still feel obliged to somehow give a motivation because maybe this will also be online, I don't know. So I will briefly run through this, but I believe that you probably also agree that this is interesting enough. And I'm coming, obviously, given that this is SU2 to the n, I'm coming from a quantum computing background, and hence my introduction starts there about how do we compute classically. Well, if you think of a computer, then you think of something that takes an input, gives an output, and this output is a function of the input. Of course, this is a little bit too simple because we don't want to just think about a computer, but a universal computer. So we also usually give it a program, right? And or instructions. And now a computer takes a set of instructions and an input and generates an output. And now we can call this universal. And yeah, this is what this will be about, of course. We call this universal if there exists a set of instructions for all input-output pairs, basically. And then we can do the same for a quantum computer, except that now we are not in a binary space, but we are in a Hilbert space, and we have unitaries. And I know this looks now like I'm going to say something about no programming or whatever, but I don't really care at this point. This is just a motivation, right? So I'm taking a unitary and an input, and my output is basically the application of this unitary, and I call this universal if there exists a unitary for all input-output pairs. Okay, so now I have this kind of unitary, and I found some that is really, really exciting. I'm a theorist, right? I run to an experimentalist, and I found this really, really new and cool circuit. And I tell the experimentalist, hey, let's implement this and get rich. Very new, of course. Maybe I'm a few decades too late, but the experimentalist doesn't really think in this picture necessarily, right? The experimentalist, maybe an iron trapper, thinks of, well, laser pulses, right? So I need to kind of a little bit adapt my picture, not think of just one big unitary, but I have kind of an easy answer, right? Which is like I decompose my unitary in many small little bits and so on. And if I do it right, then the experimentalist will be saying, yeah, okay, I know exactly what you mean. So you mean here we have a Hamiltonian that we apply to our system for a certain amount of time, and we repeat this many times, except maybe not the same one twice there. And yeah, and then this, of course, and now the motivation will end soon, luckily to you all. This is, of course, the correspondence we are looking for. That is, we have unitaries on the one hand, we have observables on the other, and this is, of course, the correspondence between Lie groups and Lie algebra by the exponential map, right? And with that, like theorists and experimentalists live happily ever after, and I end my motivation here. Actually, it's a nice ending for the talk, just generally, so I could stop here. I find it nice, but of course,
Any questions?
Do you have any further questions about this part? Yes. So no, of course, this is where we actually begin. Okay, so this was the title, and I want to go through this title step by step, and want to introduce the necessary quantities here for this talk. So, well, by now you should know what the Lie algebra actually is. So it's the vector space of skew Hermitian traceless 2 to the n squared matrices, along with some kind of Lie bracket, which is just the commutator if you think of matrices. And then in the title, okay, this covers this of the title. I will color code it in this way, apparently, for the rest of the talk. And then there will be also the Pauli strings. So I'm focusing on these Pauli strings on n qubits. And these are just our, well, these are the Pauli operators and tensor products of Pauli operators, except that we always exclude the identity on all for convenience. So, and they are related. I'm not just putting this there for nothing, because obviously this Pauli, this group of Pauli strings is actually a basis of the algebra, of this specific algebra. Okay, so great. So if we take this, then we also know that any unitary, so any element of the Lie group, can be represented in this way, since it is a basis. And then there's, given that we're working with Paulis, and Pauli strings more specifically, there's some interesting things that we can make use of, which is like the Baker-Campbell-Hausdorff formula and some specific applications of it, like this one, where we can actually, in the Lie group, which is the one we are interested in because we are always creating unitaries, we can also create commutators of these Pauli strings. And the nice thing about the commutator is that it's either 0 if they commute, or it is the product of these Pauli operators if they anti-commute. This is true for Paulis. Okay, then we want to talk about generating this Lie algebra, right? So, and in order to generate this SU2 to the n, we are looking for a subset of Pauli strings. We're talking about Pauli strings, right? Such that the real span of all possible commutators of commutators of commutators of commutators of these Paulis gives us the Lie algebra. So this kind of sets the ground, the framework for this work, really. So, and we can make one simplification if we look at it, since we know it's a basis. Let's just remove the span. Let's just look at the commutator of commutators and see how many do we need to generate the whole Pauli group, so every element. So this is where we start. Okay, I hope you're still with me. And now the rest of the talk will basically be about doing this optimally, right? But I want to make one comment, because I think it's important. For this talk, this is really crucial, right? Because we heard yesterday already that there's actually, you can, we had an answer to this question, well, not the optimality part, but we saw that actually if you have two local rotations, so all local rotation for 2 qubits, and you have a global Heisenberg interaction, you can do everything. That's SU2 to the n, right? But the Heisenberg interaction is not a Pauli string. It's a sum of Pauli string. We are excluding this, because otherwise the answer would be already bounded by 5, right? Because this would be xz on 2 qubits, 4, that is, and then a Heisenberg interaction, that's 5. Okay, and in fact, there's a known answer for this question, for the smallest set. And some of you might know, it's not 5. If you look for the smallest set, it's actually 2. And I think the first occurrence, and please correct me if I'm wrong, because I'm always curious about this. I think this is the first time I have seen this being proven, that 2 are enough to generate the whole Lie algebra. This is like from the 1950s, something.
And it was echoed by Seth Lloyd.
Yes, Seth Lloyd, I think on top of that, he said something about just take 2 random ones from the whole space and it's also holds true. This has an actual explicit construction using like the Cartan subalgebra and stuff like this. So I found this, I was very happy when I didn't find it, a student found it. It was pretty cool. Okay, but this warrants also the question, why do we actually use Pauli strings, right? Why do I care so much about them, right? Because mathematicians apparently don't care. They cared about Lie algebras in general and find a solution to that. But I care about Pauli strings, which is a subset of those, I guess. So I think they're theoretically interesting for not only fermionic simulations, but general for quantum simulations. They're, to me, I mean, there's many reasons theoretically why they're theoretically interesting, but to me specifically, they're interesting because they appear naturally in measurement-based quantum computation, which is where I come from. And then you can add everything that Jens already said, for instance. And then, of course, they're experimentally interesting because in some architectures, they appear as native gate sets, such as ion traps. And they are simple to deal with, right? I'm no mathematician. I don't come from the quantum control theory or whatever, so I need something that is easy to work with. What makes them so simple is that they have very nice representation over the binary fields, right? There's a representation over binary fields of n Pauli strings that is 2n dimensional. And there's the Clifford tableaus and many other things. Okay, now we can move to the results. Are you ready? So the question here is, what's the smallest set of Pauli strings that generates all others? And maybe some of you have already seen the poster by Gerard, and if you looked really hard at it, you would actually see the answer there too. It's a consequence of what they also did. We did it in a different way though. And this to just rephrase it a little bit more mathematically, it's like, what's the minimal size of a set of Paulis such that all possible commutators of commutators gives me the whole Pauli group. Okay, anybody wants to take a guess what the answer is? We actually found, if you know this one, you already have kind of a lower bound, because we know that the Pauli group can be represented in this symplectic vector space, which is 2n dimensional, right, for n qubits. So we know if we could do products, then it would be 2n. But we can't do products. What we've seen, we can do commutators and commutators of commutators. But these are products except when they are commuting, then they're 0. So the question is, do I need to add something to this to make this as powerful as a full product? And the answer is yes. So with n you were very close, but you only need to add one more Pauli. So to show this, there's two things we need to show. One, we first give a construction, and this one might be interesting to some of you, to actually construct these universal sets that have this specific size, 2n plus 1. And then the other side is to show that any set of size 2n fails to generate it. Right? I will focus on the left. The right one, I will give a brief overview of how it works, but it's fairly simple once you know this notation, but I will not go into detail. Okay, let's go through just a really quick example because I always find it useful. So we have 2 qubits, and we have this set. Do you see actually this? Does it help in any way? Probably not. We have this set. This is 2 qubits. It has 5 operators. So in principle, after what I told you, this could be universal, and in fact it is. So if you look at this, we can also see. We can go through some examples. Y is just the commutator of this. The other Y is a commutator of this. Then we have XX is a commutator of commutators, like this. And we can go on like this, and we find just by construction, so to say, we find this works. Okay, let's go to the more general construction. Let's start with n qubits. Okay, so this is what this will be is a sufficient condition, right? I will give you a construction with which you can always construct universal sets that are also minimal. Okay, but it doesn't say that it is not necessary, right? But it's a nice construction. So you start with n qubits, and then let's pick a subset that's larger than a single qubit, but of a constant size. Okay, and we pick a set that is universal. So for instance, this one. For 2 it works. Okay, like this one, exactly. And then on the rest, we pick another subset in a specific way, namely such that this set is product universal, meaning we pick a basis of this 2n dimensional vector space that I talked about before. So it's fairly easy to construct any set like this. Okay, so we take that product universality. It has to be product universal, and then we need to extend. I don't know. This comes next. We take this first. Let's start there. We take this. This is an example. So this is how this looks like. If you look at the 3 here, it's just z and x. Next one, it's y and z, and then it will be y, y, z, y, y, x, and so on. Right? And this turns out to be product universal. So you can get any Pauli out up to a phase if you multiply them together. It is easy to show and easy to create. Okay, now comes another important part. Well, this is a trivial part. We extend the set A to the rest just by identities. But importantly now we need to extend B to the first part where A acts with something that is non-trivial. So with this operator PB that just cannot be identity. So we take a product universal set here and then we make it kind of non-local. We could have picked a local one, but we make it non-local by also make it act on the first 2 qubits here. And this will be important and you will see why in a bit. And what we can show is that this is a universal set always. And by construction it has size 2n plus 1. Because if we pick here this set which has 5, and on the remaining n minus 2 qubits, we can choose something as product universal, meaning we need 2 times n minus 2, so n minus 2n minus 4. So we put them together, we have n plus 1, 2n plus 1. Okay, so this works, this is a nice construction, good. Now I just state the minimality result, which is pick any set that has size 2n. You cannot generate the whole Pauli group. And the reason is there's 2 cases, just to have it mentioned at least. There's 2 cases. One case is where everything anti-commutes with everything else. And this is the free fermionic case that we have heard about earlier, basically. So this doesn't do for SU2 to the n. And then there's a case where at least one pair of operators commutes with each other. And what you can show is you cannot create this commutator using all the others. And this is maybe it's not. I wouldn't say it's trivial. It really is not. But once you go down into this notation with binary fields, it actually becomes clear why this happens. Okay, and just to have I want to have 2 examples why this construction is interesting. And because to me it's also interesting as a theoretical tool. Not only to show, hey, 2n plus 1, it works, great. I mean, that's cool. That would be enough for me, but it's also a theoretical tool in the sense that I have a nice way to prove universality now, which is something that I've done a lot as a quantum computer scientist. I have tried in MBQC a lot of times to prove that a set is universal. So, and this actually can help. Because what we can do is we can look at a set. So let's ask this question. Does there also exist a minimal set that is too local? So this clearly cannot fall into the construction I gave before because they are local. So they cannot act on the first 2 qubits, right? Or first k qubits. But well, we can start with a set that we've seen before. Okay, this is the statement. Let's pick these local operators. There are 10 to n plus 1, so in principle possible that they're universal. And we want to show that these 2 sets are universal. So nearest neighbor interactions and then a universality on the first 2 qubits. And the way I can now prove this is actually by reducing this problem, this set onto the set that that fits our construction. And that's fairly simple for this. Because we have seen that this one was universal. That was the example I've shown to you. This fulfills everything that we said before. So we still keep A, and then this is the set with y, 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 z. This y, 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 x is kind of Majorana construction. and then we put this on A, and we know that A and B are universal. That was just the previous slide. So now I can just write, okay, well, hey, if I look at these operators, I can actually create them by repeated application of my commutator. I mean, the commutator, it has this adjoint like representation is an adjoint operator, but this is just repeatedly applying the commutator. Sorry, I mixed this formulation here. But anyways, you can see that if I take here neighbors, so to say, all the way back, they always anti-commute. Neighbors always anti-commute because xz, so z here, and so on. And then I get always y's in the middle, and at the end I will end up with an x or a z at the end. So I've basically constructed the set that we know is universal. It fulfills all the conditions on our construction. Hence, the statement is true. I find this quite neat. We can go on. There is, in Innsbruck, we have this company called Parity QC. And they basically, if I paraphrase them, they have a specific gate set that consists of local rotations, like this, and then non-local rotations that act on 2 or multiple qubits and a certain subset of these qubits given by an index set. They usually would write something like this, which just is a local description of it. It's not so important. If you want to see more, then I recommend this bottom paper. And what you can do is now you pick all pairs. So let's say you have Z interactions between all pairs. And what we can show with this is also that this is universal, which they knew already, but it's easy to show in our formalism. And we can even ask for other architectures, like what if you have the index pair, so the non-local interaction is only one, a single one, which is a global one. So it acts on all n qubits. So you have local interactions and you have one global interaction. This is universal as long as n is even, which is kind of curious. Now to the second part of optimality. Or are there any questions about the first part at the moment? And this relates to your question, Robert, right? So how long is the sequence of commutators such that I can create any other Pauli from it, right? So in other words, let's pick a minimal generating set as we had it before, so 2n plus 1. So what's the minimum number of operators I need such that if I, for any Pauli, like what is the R such that, what's the largest R such that this can generate, what's the minimal R, sorry, such that such a sequence can generate all Paulis, right? This is basically your questions, right? Question. It's ON, yes, correct. And this is true specifically for the construction we are having. That's why I said the general sets as before. Okay, so and the way how we prove it, in fact, also how we prove the construction is basically by we're given an explicit algorithm that does it. So this algorithm, we call it Pauli compiler. You input a target Pauli that you want to reach, and what it outputs a sequence of Paulis of your generating set, such that their repeated commutator gives you your target Pauli. And this compiler itself is probably not optimal. I can see you can probably improve it. It runs with n squared runtime. And what is nice is that the length of these sequences as outputs is always ON. Okay, and now I would like to give an example of how this algorithm works. This does neglect some edge cases that the algorithm has to handle, of course, but it captures the idea of how it works. And it's all, you will see, it's all about the specific construction we chose. So, we start, as I said, with the input, which is our target Pauli. I specifically separate them here in V and W, where V is now this forma, this constant size set where I have a universal, where I have the universal generating set of SU2 in this case, and SU4, sorry, and the W is X on the rest. This will be important, and I have my generating sets here. Okay, so the step one, and I will go through an explicit example before. I think I did it, unfortunately, in the wrong order. But the first step is basically we find a product of elements of B. So this is the product universal set, right? So we know there exists a product that has at most length n, such that at least on the second part, we have the desired operator, while the first part will be something. Okay, and then the problem that we are facing now, this is easy. The problem we are facing now is we want to do this not as a product, but as a repeated application of commutators. So we need to make sure that nowhere in this application of B's, they ever commute. But we cannot make sure that this happens. So, but this is where this universal set on the qubits in this A set come in. That is, we can actually add elements of the set such that it ensures that this commutator is not zero. It's basically because it is universal. And yeah, we also have to ensure that this is not identity, but this is not so important. Exactly, and then this time we get again some other V prime out that is neither V nor V prime necessarily. And then in the last step, which is easy, well, since we are universal on this A set, we just find a set on this A such that we can map V prime to V. And since this set only acts on itself and never on the B part, we're done. So, and as an example, let's take a specific set. So our target is this, okay? Some operator. And let's take as a generating set, we take this, we have our helper system, which is the one that you've seen before, and then we add something that's product universal on the other two. In this case, I just I basically ignore the ones because that's just how I extended to the first set, but I basically pick something that has the local operators, Z3, X3, Z4, X4, and I could continue like this. Okay, then what does the algorithm do? Okay, it first has to find this product on operators on the second half, so Z3, X3, Z4, X4, such that it coincides with Z3, Z4. That is, for instance, we pick Z3 and Z4. It's trivial. Okay, and now what we see here is that they actually commute, right? So I cannot really create this product. So what I do instead is now I have to add something from the helper system such that they anti-commute. I can do this because I have non-trivially extended this product universal set onto the first, right? You see this here. So all I have to add is, let's say here, an x1, right? And then suddenly it's the commutator of these three is no longer 0. But now I'm ending up with an x1 on the first, but I want a y1 on the first. So what I do is, again, I use something from my helper system to make this a y in this case. Is that? That's how it works. And it's nice because you can show that it has a runtime, which is n squared. You can show that the sequence you output is always linear in n. And well, you can use it to prove that these sets always are universal if you're given these conditions. Okay, but there's a subtlety. And now I unfortunately do have to come back to constants, which is, if we look at the efficiency of how well these sets generate the whole basis of Pauli's, then they will of course differ. They will differ by some constant factor, or even worse, something else. Why this is the case, I will tell you in a second. So these are three sets, where the top one is kind of what we would call the standard gate set of quantum computing, where you have nearest neighbor interactions, right? And this is not minimal. I think this is not minimal. No, it's not, yeah, because you have all local ones. So it's not minimal. So, and the cool thing is that even though it is not minimal, and we are allowing much more interactions that we actually need, there are still some sets that generate it faster. And the example 1, this is the one that you have seen in the example that I've given, and then we have the local interaction for the example 2. So the local interaction, what you see is actually that they need n squared time. They need n squared operators to generate all. And this is kind of curious because nowhere, like in our proof, we have shown that our construction is kind of the best. But it seems the naive way how you would do this is the one that I've shown. You, whenever you want to generate something, you first take these and you map it onto this set, an element of this set, and then you run our algorithm. But that is a run time of n squared and seems very naive. But it seems that actually that's the best you can do for this local set. That you need to first map it onto something that's non-local in the worst case to generate all your Paulis. You need to map it onto something that's non-local, and then you can kind of apply our algorithm. So, yes, and I will not talk about the example 3 much, except in the outlook at the end. Okay, so constant factors here. And so this is quadratic because of its local structure. And of course here, this has also local structure, but it has much more operators than we are typically given. And it's much more than 2n plus 1. Okay, so let's talk a little bit in more detail about this efficiency of generation. So it seems that this efficiency of generation is somehow linked to the anti-commutation graph amongst the generators. So, what follows, we're kind of assuming that, let's simplify it and just assume that all generators anti-commute with a constant fraction of all the others. And so, for example, we have if they all commute with all others, then this is a very boring graph, a very boring generation, because you cannot really do anything, because well, you cannot generate anything beyond the generating set. Okay, but if it's 1, you would think that having a lot of anti-commutation is good, but at 1, this is of course not ideal, because then you can generate a lot of new Paulis in one step, but after this one step you are done. Which is basically also why this kind of gives you like this free fermion models. Okay, but we can actually make this more rigorous and find a optimal fraction here for these Paulis. And we can both do it algebraically under the assumption that I've just given you, and also numerically by just generating sets that have a certain fraction. And what we see is that the optimal rate is somewhere here, right, up here. So the standard set is by far not the optimal to generate all others. Neither our other examples, but this curious example star, which I will mention at the end. And David is probably very happy to explain to you in more detail. Exactly. So yeah, this is the one that I want to reference. I did reference it in the end. So yeah, as I said, David wants to talk about it for sure with you. And it's basically, it has a very cool construction in terms of these Clifford's quantum cellular automaton. Okay, you would think it's kind of at 1/2, but it is not. The optimal fraction of between how many all generators you want to anti-commute with each other is at about 70%. Right? So it's my intuition, as David's also, would have been at around 50%, I guess. Right? But it's apparently not. Right? And there's actually an argument that you can make. Why is this the case? I'm not going to make it here now. Yeah, and with this, I'm at the end. I will give a brief summary, and then I will discuss some outlooks a little bit longer, because I think I have still a little bit of time. Okay, so what we've seen now, the first part where I gave a construction, this is kind of a sufficient conditions for a set of Paulis to be universal. That's already nice. We could prove that the minimal size of a universal set is 2n plus 1 if you're only considering Pauli rotations. And again, not Pauli rotations, you can go down to 2. And we also gave, for this specific cases, an efficient compilation algorithm, but it seems also that this kind of algorithm, at least complexity-wise, does something fundamentally right, because even for the local cases, the best you can do is reduce it to a global one, apply our algorithm. So there's more behind it, I think. And I'm happy to discuss this. And then we gave away to what are you looking for if you actually want the perfect universal gate set, which is this fraction that I was talking about, the anti-commutation rate between operators, which is at 70%. Okay, and now just very brief, like I think three outlook cases, things that we are currently working on. So there's one part of this I've already shown, which is this kind of parity architecture, which is a very specific gate set, namely those with local interaction and then non-local interaction. We are working on this to see what kind of universal gate sets you can get out with this. And then beyond that, we are actually working with Thierry, who's also here in the audience, about trying to map generating sets to specific graph states that implement these rotations of the generating set in a measurement-based fashion. So finding this best structured graph state. So an example of this is here. We've kind of seen it before. If you know that, for those that know MBQC, what we're doing here, this is a graph state. And now you've heard already David say a little bit about cluster states. This is basically plus states and CZs. And if you do this, but at every, let's say, odd side, you have like a star. Then if you measure the star in the YZ basis, you get basically a global Z rotation out. And then from here to here, you get all local rotations, Z and X out, which is the generating set I talked about earlier, the one with the global Z rotation and then the local X and local Z rotation. And then you can make more statements about what if you separate this more and what you can do. And more generally, we are looking at algorithms that actually decompose generating sets into graph states. Okay, then maybe an interesting viewpoint you can also take is what we can do is this is a side result. This is not really that obvious from everything I said, but basically what you can do, if you give me an arbitrary Pauli and you know you have a generating set that's universal, what you can do is you can fix one generator and you can generate any other Pauli, any P, by applying Cliffords of the other generators. And this works for any. So you fix one and then every Pauli here can be created in this way. No? Okay, and how you can see this is actually something that in last year has also been considered, which is you're implementing certain algorithms in a swapless way. Because a lot of algorithms actually rely on you swapping or shuffling qubits around, but you can do better if you have the right generating set. You don't even need to think about swaps, which is kind of nice. In this paper, for instance, this is the parity people that I was talking about earlier. They show that you can, for some algorithms, there is kind of you get some advantage, I mean not a complexity advantage, but an actual practical advantage by not using swaps, but using Pauli rotations and even non-local Pauli rotations. Another point of view you can take is, hey, I just told you these are pi over 4 rotation. These are all Cliffords, and in the middle there's one non-Clifford. So I can fix it, this one non-Clifford, for instance, to be a T-gate. And then I can use our algorithm to construct any other gate from this using only these Cliffords, this Clifford generating set. And it might inspire also, this is related to the quantum cellular automata generating set. I was earlier saying this kind of inspires a point of view in fault tolerance that you can take, which is the stacked codes construction by Bombin from 2016, where you take a bunch of color codes, which are 2D, and then you put a 3D color code on top. So the whole thing is still 3D. And what in this paper, what he does, he can show that you can always swap information around. In this way, you can be universal. But I can now say even better, you can actually do it in a swapless way. And this might offer actual advantages. Okay, and then, and this is the last thing, the perfect gate set. Right? So there's this regime, we've seen it. We come close with this construction by David, which has about, it's around, I think, a half, if I remember correctly. Yeah, it's around a half. But what is the perfect gate set? And I think this is it's a nice conclusion, and I offer this as a beer challenge. So if you can come up with a generating set of Paulis, which has this fraction between them, or a constructive way to come up with them, of course I offer you a beer and a paper probably. So probably more fitting for Hanover would be a Kasten. So not only a beer but a whole set of beers. Yeah, and with that, let's please discuss, ask questions, or meet me wherever, or any of these collaborators. This one is here actually, right? And thanks for your attention.